So in this part, you will see that I've already drawn a drawing. And there's this thing called the valence band. So if the term valence is new to you, if not, then you would think to yourself, oh, hey, I know the term valence before. Valence electron is the electron in the outermost shell. So valence band is the electron in the highest energy level. Okay, so this valence band here, valence band is the energy band of the electron with the highest energy level. And although this drawing is a little bit imperfect, but what is happening here is that your valence band overlaps your conduction band. So there's a region of overlap here. So you can think about the valence band as slightly thicker. Okay, and this region here, this part that I'm going to highlight yellow, this is the overlap. Okay, so the second thing you notice is that there's an overlap. Overlap with what? Conduction band. But what is conduction band? Conduction band is the energy of the electron which are mobile enough, that is sufficient, mobile enough, that means you have enough energy to carry charge and current. So for a metal, right, it's very straightforward. I don't need the conduction band to be so high. Okay, because if you think about metal, right, the outermost shell, we at most will have 1 or 2 valence electron. Metals are group 1 and group 2 elements. So they already have very few electrons on the outermost shell. And these electrons, because there are only a few of them, they're actually very free to move. So the conduction band is at a lower part compared to, let's say, if you look at semiconductors and look at this insulator, my God, conduction band is so far. Okay, so let us try to describe the bands first. Okay, and then here we will say that the valence band. So for some description, because sometimes you need to use the description in your explanation. All right, so if you understand this picture, okay, you can describe the valence band and the conduction band. So number 1, valence band, I will use the short form VB, overlaps conduction band. I will use the short form CB. Okay, and because of this, number 2, the the forbidden band doesn't exist. Miss, what is a forbidden band? Okay, let's go back to the original band diagram. This case, you see this empty space here where the electron cannot pass. Here is forbidden. But what we are drawing right now is not the 1s. No one cares about very close to the nucleus. Let's say your atom stop here. We care about here. So if this is example only, if this is the atom that you're talking about, here is your valence band. An electron at the highest energy level. The bottom one confirm cannot help you carry charge. Okay, think about electron as charge carriers. Do you remember? You know, electrons are your charge carriers. So they need to have enough energy and enough mobility to help you carry your charge. So this means if the valence band and the conduction band overlaps, so let's say I draw the conduction band here. The conduction band overlap. Some electrons are already conducting electricity for you. This is overlap. Okay, whatever that is in between here, this is forbidden. So the forbidden band is here. And there's no forbidden band here. Between the valence band and this orange color thing is the conduction band. Okay, so there's an overlap. Right, so we're going to move this into your notes. Okay, so we will say that the forbidden band, I'm just gonna write this as FB, doesn't exist between the valence band and the conduction band. Okay, so it doesn't exist. And the overlapping is here. Here to here is where valence band overlaps conduction band. And because of this overlap, there is always charge carriers, electrons. Electrons are your charge carrier. If your electron is inside the conduction band, name also conduction band already, it can move for you. Okay, so electrons inside the conduction band are available charge carriers to help you conduct electricity. So that's why this is a conductor. Beautiful. What happens for semiconductors? Semiconductors is where you're talking about, okay, I'm going to give you some examples here. So conductors examples are like metal. And if you do chemistry, we are looking at group 1 and 2, maybe 3, group 1, 2, 3 elements. Group 1, 2, 3 means you have 1 valence electron, 2 valence electron, or 3 valence electron. So when the valence band does not have that many electrons, the conduction band is closer to the valence band. All right. There are more nuances here, but I don't want to go deep into it because it's chemistry. We're going to move on to semiconductors now. So examples of semiconductors, if you remember, are like silicon. Okay. And this one is normally group 4, 5, 6, and all your transitional elements. Things get very complicated after that, right? So somewhere there lah, okay? And we tend to use this in a circuit. Let's think about this. Of course, it's probably fairly straightforward to see what kind of conductors are in your circuit. Metal ma, so we make metal wire lor, metal resistor lor, filament lamps lor. So I'm going to change color and put here. So in a circuit, this could be wire, filament. Okay. What about the other one? This one. In the circuit, what are semiconductors? All right, you have two types. Okay, so semiconductors that we will talk about that is made out of silicon. You will have your thermistor, okay, which is affected by temperature. You remember, right? We just did thermistor not too long ago. And your light dependent resistor. Oh, miss, are these the sensors in your op-amp? Yes, LDR. Okay, so what is the difference for this energy level band compared to the conductor? I think the first thing you notice is that there is a gap. Ooh, do you want to guess the name of this gap? Okay, this gap here is the forbidden band. Meaning there can be no electron can be here. It's forbidden. All right, so if the electrons want to conduct electricity, but they're all in the valence band, we got to give it a boost. We got to give it some energy so that it can jump into the conduction band. But the good thing here is that the forbidden band is very narrow. And when the forbidden band is narrow, it may have energy to jump from the valence band to the conduction band. This meme needs fixing. Okay, so if there's enough energy, the electron is getting to jump from the valence band to the conduction band. All right, and you need the gap to be just right. Even RuPaul is waiting for it. So here, this is your forbidden band. We need the energy to transition. But what can provide that energy? Okay, put a pin on that top. Put a pin on that top. Yeah, put a pin on that top. And then we are now going to describe the bands first. So description. And this description is only at 0 Kelvin. Okay, of course, when the temperature increases, things will change, but this is in 0 Kelvin and kind of like absolute darkness lah. All right, so what happens to the valence band? Number one, the valence band is fully occupied. Fully occupied by the valence electron of all the atoms inside your sample. Number two, the conduction band is empty. And number three, the forbidden band is narrow. And the energy level and the gap size is more or less 1.1 eV. Around 1 eV lah. Okay, so this forbidden band is narrow. Okay, so if the forbidden band is narrow, what does this imply? A narrow forbidden band, meaning that the electron can actually jump into the conduction band. But we need to give it an energy. We need to give it a boost. All right, so I'm going to write down here what could possibly boost the electrons. Okay, so number 4, if the electron is given energy, or enough energy, sufficient energy, it jumps into conduction band from the valence band. Okay? Jumps into conduction band from the valence band. Jump like this. So what are the possible ways to give an electron energy? You know this. We talk about this. So to add energy, I have 2 options. Option 1, I can increase temperature. That's why I put this at 0 Kelvin. So once I increase temperature, the electron will jump. Option 2, I can increase light intensity by giving our little electron some photons. So I can send photons over or heat. Electrons are like, you know what, dude? As long as you give me enough energy, I'm very willing to jump. You could either increase the temperature or increase or shine some light. Okay, but the consequence of this electron jumping, you can see the electron is here. This electron is negative charge. Okay, cannot really tell from the drawing. Let me fix it a bit. This electron is negatively charged. And think about what happens when the electron manages to make a leap. A giant step for electron, a tiny step for humans. Okay, the electron jumps into the conduction band, but what does it leave behind? What does it leave behind? You left, electron, you left us, leaving behind a hole in the valence band. Wait. What is a hole? What do you think a hole is? A hole here, if you've watched the video, if not, I will define it for you. This hole is known as the absence of electron. You remove the electron, you leave an empty space there. The empty space is hole. Okay, so you can go and ask someone out and say, if you don't go out with me, you leave a hole in my heart because you are absent. Okay, so this absence of electrons implies that the hole is positively charged. Positive charge. Electron is negative charge, hole is positive charge. And of course, you may be thinking, is hole a charge carrier? Why, I'm glad you asked, because the hole is like, hey, don't forget about me. I'm also a charge carrier. I mean, my brother, the electron, is more showy, but I am a charge carrier too. My brother is more showy, and he moves around a lot like a squirrel. But I too am a charge carrier, says the hole. Okay, so the hole are also charge carriers, right? So this one becomes charge carrier. Suddenly now you have two charge carrier. You have the hole, which is positively charged, which is now your charge carrier. And you have your electron, which jumps into your conduction band. And this electron is also charge carrier. Wow. Many charge carrier, insert sound effect. Wow. Many charge carriers. When you increase the charge carriers, what happens to your conductivity? You're more able to conduct electricity. So as more and more electrons do the transition, not the TikTok transition, but the electron transition, across this narrow forbidden band. Look, electron cannot be in the forbidden band. So the electron, as they all transition, there will suddenly be more and more charge carrier, leaving behind more and more holes. This is why the resistance will decrease. Okay, so I think now we can write the essay explanation for this part. Okay, so we are going to now write down here, or at least is what I'm going to try to do, to write the effect of temperature and resistance. Effect of temperature and light intensity. Intensity on the semiconductor. Okay, so this normally, right, is a 5-mark essay question. So you got to write out the points carefully, okay? And the reason why I put it together is because sometimes when you want to study an essay, you want all the main points in one page, not in several pages, especially if you're doing your notes. But before we write out the essay, we got to plan a bit. So I'm going to now draw a flow chart. Okay, we will draw this flow chart to help us sort out the information. So just now we've learned that thermistor, number one, to increase the energy of the electron in the thermistor semiconductor, we will increase temperature. So you will say something like temperature increase. Whereas for LDR, light intensity increase. Okay, so what happens now is number two. This one, the electron gains energy. And the other one can be a bit more specific. Electron gains energy from the photons. All right. So if you're wondering where the electron gain energy from when temperature increase, this is from the lattice vibration. Okay, because when you heat something, they vibrate more. So the electrons will have more energy. But the effect is less pronounced than the LDR. Okay, so I guess we can say from lattice vibration. All right, so this is where things are a bit different, but then the consequence of it, because the band theory for both the band diagram or the energy diagram for semiconductor, thermistor and LDR look the same, right? So then in this case, they will have a similar explanation. I'm going to draw a line here. Okay, so point number 3, you can say now the electron have energy either from lattice vibration or from photons. And because of this, you can say that the electron jumps into the conduction band from the forbidden band. Okay, so the electron jumps, not from the forbidden band, jumps into the conduction band from the valence band across the narrow forbidden band. So you can write something like this just to show that you really understand the band theory. Okay, so the electron now, because it has energy, it will jump into conduction band from valence band across forbidden band. All right, so what happens when they jump into the forbidden band? Okay, number 4, leaving behind a hole. Remember a positively charged hole? Bloop. In the conduction band. in the valence band. All right, and because of now you have electron inside the conduction band, and you have this bonus called holes. So number 5, you can say that hence there are more charge carriers in or exist, just more charge carriers. Okay, so because of this, decreasing the resistance of the material. Oftentimes they will ask you what is the effect of the resistance. This is the conclusion, decreasing the resistance of the material. So in this case, for LDR, we close shop. So LDR is very straightforward. Electrons in valence band, not enough energy. Shoot some photon, got energy, jump into conduction band. Hole left behind. Since electrons and hole are charge carriers, since electrons and holes are charge carriers, so there is more charge carrier, decreasing the resistance. Okay, but there is another extra point that you have to write for thermistor. Because the thing about heating up something, right, is that the lattice will vibrate more. Or in other words, the atoms will move more vigorously. That's why the electron will gain energy through lattice vibration. So this lattice vibration, you imagine the entire atoms will begin to shake, the nucleus will begin to shake more vigorously. You might think that, Miss, if the lattice vibrate more, wouldn't that make the resistance higher? Because it's harder for the electron to move when there's a big earthquake inside the material. Well, that effect is not as pronounced as increasing the number of charge carriers. Because previously you don't even have any charge carriers, or you only have a few. But now you have many, many charge carriers because that vibration shakes up the electron. The electron can jump into conduction band. So this effect is more important or have a larger impact compared to the lattice structure. So that will be the 6th point that you need to write. Okay, so the 6th point here, you will say that the effect of the increase in the number of charge carriers is, or you could say outweighs, more pronounced, outweighs the effect of increase in lattice vibration. So resistance still decrease. All right, so this is the 6 points for your thermistor. Do you need to write everything? Yeah. This first 2 is normally 1 mark one. Okay, temperature increase, electron gains energy, 1 mark. Okay, electron jumps into conduction band from valence band, 1 mark. Leaving behind a hole, 1 mark. Okay, so we have more charge carriers, 1 mark. But the effect of increase in the number of charge carriers outweighs the effect of increase in lattice vibration. So although the lattice vibration will affect the resistance, maybe decrease it by 10%, the increase in number of charge carriers will have a larger effect, maybe 40%. So at the end of the day, the net effect is still decreasing resistance. This is the 5th mark here. Okay, so when you read and answer the question, you have to be very specific about what they're asking for. Sometimes they ask about the LDR. Then you write these 5 points or 4 points. Light intensity increase, electron gains energy from photon, and this one is all still the same, 1 mark each. Okay, the only difference is that for thermistor, maybe you increase the number of charge carriers, the resistance decrease by 50%. Sure, the lattice vibration is happening, but maybe the lattice vibration effect is only 10%. 10% increase, 50% decrease, the net effect R will still decrease. Okay, so this is the essay that you need to write and that I cannot fit here. Okay, or at least I will try. Okay, so that concludes the part where we talk about the effect of temperature on the thermistor. Temperature increase, electron gains energy. And the light intensity on the LDR. Temperature on thermistor. Because these are all still semiconductors. Light intensity on LDR. Okay, so the starting point is a bit different, but after that, when you talk about band theory, okay, like for example, the electron will jump into the conduction band, leaving a hole behind, so we have more charge carriers. Okay, and the effect of the increase in the number of charge carriers will outweigh the effect of the increase in lattice vibrations to the resistance. So at the end of the day, your R still decreases. Okay, so now we're gonna think about why this is important, because we want to have these things called our sensors that we use, but also what about metal? What happens when we heat a metal up? Because it's not fair that we only talk about the semiconductors, right? Although this is where the chunk of the past year question is. Sometimes they will ask you, hey, you guys, since the thermistor, when the temperature increase, the resistance decrease, will the same thing happen for my metal? What do you think? What happens when you heat the metal? Lattice vibration also happen. The entire metal structure goes through more vibration. But do you get more charge carriers? Unfortunately, the charge carrier already exists. The valence band already overlap. There's no jumping necessary. So your resistance will increase one. Okay, if you remember from your chapter 19, your IV characteristic, resistance of filament lamp will increase with temperature. Okay, so now we're going to also compare this by writing now the effect of temperature and resistance of metal. Okay, so we're going to start off first by talking about the effect of changing, increasing the temperature to the lattice structure. Okay, so you can say that as temperature increase, there is more vibration to the lattice structure. Okay, so because there's an increase in vibration to the lattice structure, number two, we can say that since our conduction band and valence band overlaps, so always use the band to explain. Like for example, here I use the band to explain the jumping or movement of electrons. Now I use the band theory to explain what happens inside a metal. So your conduction band and your valence band will overlap. And because of this overlapping, number three, I say that the number of charge carriers doesn't change, because you don't get more movement of electrons into the conduction band. They already overlap. Okay. Then number four, so hence the lattice vibration hinders the movement of the charge carriers. And because of this, the resistance increases. Okay, so if I'm going to color code this, the same as this one on the left, what I will talk about is the first point is the effect of the increase in temperature, the more prominent effect. For thermistor, the more prominent effect is electron gains energy, the more important one. For metal, the electron gain energy, gain energy, it's not that important because the electron already exists in the conduction band. That's why we talk about the lattice vibration. Doesn't mean it doesn't happen for the thermistor. It does, but the effect is less. It depends on which one is more important to talk about. Okay, so then discuss the band theory and apply this to metal. So the discussion for that band theory, point 2 and point 3. Okay, so the discussion about banding is blue, blue for band, and then talk about the charge carriers and talk about the lattice vibration. Okay, so when you write about the explanation, right, always think about referring to the band theory to help you explain. So are we talking about overlapping bands or a narrow gap? If there's a narrow gap, there's jumping. What happens during the jumping? And because of this, we have more charge carriers. However, what is the effect in lattice vibration, especially when you increase temperature? If you send in some light, the changes in temperature is almost negligible. So we will not talk about that. Okay, so here is 4 marks, here is 5, the other one is, I believe, 4 as well. So if they ask, they will ask, I think they've asked two of this before. They may ask you why the temperature increase, resistance increase in metal, but temperature increase, resistance decrease in thermistor. So then you have to explain, no? Okay? Or they could ask you to explain the band theory description. All right? So the last part, we are going to look at the insulator. Now, the idea of the insulator is just to complete your understanding for this part. Okay? Your insulator, right, the band gap is super big, like very large. Okay? So this band gap, okay, the gap is very large. Sorry about the lag just now. Okay, so this is a large gap. Large, thick, forbidden band. So if there's a large and thick forbidden band, by the way, examples of insulators, let me fix this thing a bit. Example for insulators are groups 6, 7, and 8. So this one is a bit off. Technically, the classification is a bit blur for 6 lah. Okay, 6, 7, and 8, your noble gases, your polymers, for example, rubber. Because everything is locked into a tight chain, the electrons are not very mobile. So the electron needs a lot of energy. That's why the conduction band is higher than usual. Okay, so the conduction band here is higher energy because the electron needs a lot to be mobile. Why? Because they are trapped in a polymer chain. So polymers are chains of hydrocarbon, chain and chain of molecules. So if they're tied into chains, they're harder to move. Okay, so the only thing you need to know here actually for physics is maybe a band description. So you could, like for example, they could say that why increasing the temperature of the polymer or increasing the temperature of an insulator does not change its resistance one bit. Okay, so the first thing you will say is that the valence band, again, we're going to just give a basic description here. Let me move the screen a bit. Okay, the valence band, fully occupied. Number 2, forbidden band, very large. Okay. Number 3, conduction band, very empty. Empty and high energy. High energy level. And because of this, right, if you want to explain that, you will say that the forbidden band is too large or the conduction band is too far away from the valence band. So since the conduction band is too far from the valence band, increasing the energy of the electron by increasing the temperature or increasing the light intensity by temperature increase, etc. There's temperature increase or increase in light photons, okay, light intensity, has no effect. On the resistance. Sad case. So it's just will not conduct for you. I don't care if you heat it until it melts, it will not conduct for you. The forbidden band is too wide. The band gap is large. Okay, so because the conduction band is very far away from the valence band. So that's it for this video. They're not going to ask much about this. In fact, I think you can tell the favorite one would be the semiconductors. Okay, so what you need to know is you need to look at the past year question sets, and you can see that they will ask in turn either the effect of temperature on resistance of a metal, effect of temperature on resistance of a thermistor or a semiconductor, effect of light intensity on the LDR or a semiconductor, to which you can write all the relevant points. Remember to state or the structure of the conduction band and the valence band, overlap, small gap, overlap for conductors, small gap for semiconductors, and large gap for insulators. Okay, what happens when the electron jumps? All right, so this will actually help us explain why when we do experiment, when we shine a light on this material, resistance decrease. We shine a light on another material, resistance no change. You heat up this material, resistance decrease. You heat up the other material, resistance increase. Why? So we can use this band theory to explain. Okay, so in this chapter or in this subtopic, this is what you should know. What is band theory? What's the picture like? And how to use band theory to explain certain changes in resistance or no changes in resistance for certain type of material. Okay, all the questions here will be essay based. So you need to write out this explanation for 4 to 5 marks. You can refer to the list of suggested past year in the description or in the OneNote page. Okay, and then I will see you in the next one. We'll talk about X-rays. But that's it. Short chapter, a bit long video because I need to help you understand the essays. And take care. Bye-bye now.